So good afternoon, everyone. Welcome to this practice talk for VCT 2022. My name is Eleonora.isotta and I'm a postdoc at Michigan State University. And today I would like to talk about tin selenide and the effect of oxides at the grain boundary on thermal transport. Okay, tin selenide is a material that has attracted a lot of attention in recent years, especially since 2014. When it was reported that single crystal tin selenide could achieve a thermoelectric figure of merit of 2.5 at high temperature. And this outstanding figure of merit was in part due to what was called an ultra-low thermal conductivity. So there were a lot of studies in the following years trying to replicate the same results, but for polycrystalline tin selenide, because as you know, polycrystalline samples are way more practical for applications. They are cheaper, easier to handle. But the problem was that it was, despite the many attempts, none of the work managed to recreate the same ultra-low thermal conductivity that they found for single crystal tin selenide, and of course, not even the same performance. So there was a lot of debate about why there was this discrepancy between polycrystal and single crystal results. And some works pointed to possible density differences, some others to possible off-stoichiometries in the single crystal sample. But the most recent and currently accepted explanation is that of oxides at the grain boundary. In fact, tin selenide is particularly prone to oxidation, and there were several works in which they actually found grain boundary precipitates that from a chemical analysis were found out to be tin oxides. So tin oxides, in particular SnO2, have a very high thermal conductivity, and for this reason, they were believed to be the reason for an increase in the overall thermal conductivity of the polycrystalline samples. So mind that of the two kinds of oxides that we might have, SnO and SnO2, one of them has very high thermal conductivity, the other one not so much, but still higher than SnSe. And another important thing to note is that in all of these samples, from an XRD point of view, they looked clean. So the amount of grain boundary precipitate was anyway below 1%, so below the detection limit of X-rays. Despite this is the proposed effect on the overall thermal conductivity. So in light of this explanation, there was a work coming out last year that decided to put it to the test and to perform to purify a sample and getting rid of the oxides. And they have compared an untreated sample, so made the same old way, where indeed they could find some nano precipitates at the grain boundary, nano because they are in the range of 10 to 20 nanometers, and chemical analysis sees that they are tin oxide, and compare it with a purified sample through a purification process. So also in this case, the amount of oxide was not detectable with X-rays, so likely below 1%. And they have reported that the purified sample, interestingly, presents a thermal conductivity that is roughly half of that of the untreated sample. So we were very interested about these results, and we tried to take a closer look at them. And so one might argue that it is possible to interpret these results in light of the oxide explanation. To actually be able to do so, one needs to use a linear rule of mixture for the composite and assume the untreated one as a composite of 1% of tin oxides, that is what would be compatible with the X-rays. And to do so, the thermal conductivity should be, to match the results, it should be around 60 watt per meter Kelvin. There are a couple of issues with this explanation though. Because first of all, although 60 watt per meter Kelvin might be in line with a sort of average of the single crystal thermal conductivity of SnO2, first of all, there are other types of oxide, for example, SnO with a much lower thermal conductivity, and the same SnO2, whenever it was produced with a lower domain size, it has shown to have a drastic dependence on of thermal conductivity on domain size, getting way lower with smaller domains. The other issue with this interpretation is that the linear rule of mixture has been shown to not really capture the behavior of composite materials, while real materials have been shown to behave something like this. Okay, so we decided to perform some tests of our own, and in particular to see what happens to thermal transport when we tune the type of oxide, because we have seen that SnO and SnO2 have very different thermal properties. And if we tune the amount of oxide and test sample with significant and quantifiable amounts. So let's see the first case study. So in order to tune the type of oxide, we turn to DFT, and this is the ternary phase diagram from DFT of tin, selenium, and oxygen. So we are interested in tin selenide. So around this region here, we can identify three main areas. So for tin-rich tin selenide, we see that the secondary phases that we should form are tin and tin oxide. For high amount of oxygen and roughly intermediate stoichiometry of tin and selenium, the secondary phases should form are the two types of oxide, while for tin poor tin selenide, we should form tin diselenide and tin dioxide. So we decided to prepare samples with stoichiometric, tin-rich, and tin-poor compositions, because as we see, accordingly, we should stabilize different types of oxide. But there's another consideration to make at this point, because as you know, of course, when we make a synthesis, we limit the amount of oxide because the amount of oxygen, because we do not want to form oxides. So we need to understand how the phase diagram changes for very little amounts of oxygen. So we calculated the phase diagram for different partial pressures of oxygen, PO2, and we can see that for very low PO2, the oxide region do not even form, and oxygen is more stable as oxygen gas. While for increasing PO2, we first start forming the region with SnO, and then the region with SnO2, until getting to the shape of the phase diagram that we see here. So in normal tin selenide synthesis that we saw in the literature, and also with the capability we had here in the lab, we can reach a level of vacuum of 10 to the negative 4 torr, which corresponds roughly to 10 to the negative 7 atmosphere in terms of PO2. So this PO2 is some order of magnitude higher than the minimum of PO2 to have this shape of the phase diagram. So this means that with this level of PO2, oxide formation is unavoidable. So we cannot help we will have the formation of oxides. So as I said, we prepare sample in the stoichiometric, tin-rich, and tin-poor compositions. So for the stoichiometric, we see that we have all the reflections of tin selenide. For tin-rich, we also see reflections corresponding to tin, while for tin-poor, some reflections corresponding to tin diselenide. So for the tin-rich and the tin-poor, we are confident that we ended up in the desired region of the phase diagram because we do indeed see the other secondary phase. We do not see any trace of oxide, but this is sort of expected because we anyway have a low amount of oxygen. So the oxide that will form will be minimal and probably below the detection limit of X-rays. Anyway, we're quite confident that oxide should be there because we have seen in the literature that that is what is normally reported. And also thermodynamics tells us that with this level of PO2, we should form oxides. And we did not take any particular step to remove them or try to avoid them. So given that SnO and SnO2 have been reported with this very different thermal conductivity, we would be expected to see a difference in the overall thermal conductivity of the samples if oxides did play a role in thermal transport. So this is the results that we got. And I mean, apparently there's not a significant difference in the thermal conductivity of the three samples. They seem to lay in a very narrow region of thermal conductivity. For this reason, we decided to test, so despite no matter the type of oxide, they seem to lay almost on top of each other. So we decided to test the explanation with the case of a varying amount of oxide, and to test sample with increasing amounts. And so to do this, we performed the air annealings of the stoichiometric tin selenide powder. And this is the XRD pattern after 1 hour of annealing. So we can see that, for example, here, that is a location where we would expect the reflections of SnO2. We start forming a little hump, which, and we move around here in the phase diagram. And the hump here that I marked with the arrow gets more pronounced with increasing annealing time. And we move even further into the region. While after 12 hours, there's not really much difference with respect to the 6 hours. So probably the oxide layer might actually have a sort of protective role and prevent further oxidation. Anyways, we decided to take this powder here and to press it into an SPS sample in order to test what are the thermal properties. And so this is the XRD pattern of the SPS sample. So we can see that the region where we saw the reflections of the SnO2 gets even a little bit larger, and we move a little bit further into the region. So this corresponds to having a larger amount of oxide. So overall, this sample has roughly 14% of SnO2 clear and identified. So in this case, we are expected, if oxide does play a role, now we should definitely see a difference in the thermal conductivity because we have a good amount of oxide. So, however, we do not really see much of a difference again. And again, there's not really a significant difference with respect to the other sample, as well as from the samples from the literature that was reported as being untreated. So we have seen that no matter what kind of oxide and no matter what amount of oxide, at least below the 14%, we do not really seem to have significant difference in the overall thermal conductivity of a sample. So we believe that the explanation of oxide to explain the difference in thermal conductivity of polycrystalline versus single crystal samples might actually not be accurate. And so we think that maybe there could be other explanation to justify this difference. So with this, I would like to acknowledge all the people that participated in this work, in particular my advisor, Professor Zavolking, and all the Zavolking group, and collaborators from Northwestern, Professor Jeff Snyder, and Michael Toriyama, who performed the DFT calculations. Thank you for the attention.